panelists, my name is Christine and my topic for the FYP is the investigation of weld defect repair using friction stir additive manufacturing. So for the content, it will cover 5 scopes, which is the problem statement, the objective, methodology, result and discussion, and also conclusion. For the first part, problem statement, the reason why I'm doing friction stir additive manufacturing for repairing is because the rate of damage of weld is high. The average repair rate in oil and gas and power industry is in the range of 1 to 3% each year. And because fusion welding will cause a lot of defect in the weld material, including porosity, crack, and deformation. So for FSAM, it has 3 advantages over fusion welding, which is first, it has lower temperature compared to fusion welding. Second, it doesn't have melting and solidification state during welding, and third is because of its flexibility. So for my objective, I'm supposed to done the FSAM process in the lab of FYP, but due to MCO, my objective have changed to first to analyze the available literature of FSAM application in welding repair. Second, I will predict the welding performance of SSAM using the current literature result. And third, I have already performed the pilot test of SSAM in FYP before MCO. For methodology, the first part is the methodology for literature review part. And I searched for the available and suitable literature study and I research and review them. Secondly, I compare the result, and third, I do the data analysis using Microsoft Excel. Finally, I'll predict the result, the possible result for according to the data of my research. For the methodology of pilot test, first I prepare the material. The material used for this research is aluminum alloy 1100. Secondly, I produce the tool by using turning process. The tool material for this research is a tool steel H13, and the features of the tool pin is that it has 4 mm plain cylinder with 5 mm right-handed clip. And third, I do grinding on the welding material, the workpiece. This is to simulate the groove defect on the workpiece. And finally, I done the pilot test by using CNC machine. So for the result part, as I mentioned earlier, the result part will be in four different scopes. The first one is I compare the result in terms of tensile strength. Second is I compare the result in terms of micro hardness. The third is I compare the result in terms of microstructure. And finally, I discuss my pilot test result. The first part is the comparison of tensile strength. 4 experiments are taken to be compared. Experiment 1 and 2 are FSAM, experiment 3 and 4 are friction stir welding. The reason for this is because it doesn't have enough literature available about FSAM for repairing alone. That's why friction stir welding are also taken to be compared. And also, in terms of tensile strength, the theory of friction stir additive manufacturing and friction stir welding are compatible. That's why friction stir welding are also taken to be compared. And finally, we can see from the result, in all experiments, the tensile strength increased after neither FSAM or friction stir welding. In the table, I also listed some of the data, including the important data, including the rotation speed and welding speed of each experiment. And the percentage change, how I calculate is I took the value after minus the value before and divide by the value before. And for the data analysis, I done by Microsoft Excel. So by using the features in Microsoft Excel, I can find out the correlation between each factor. So as you can see from the table, the highest correlation is of the percentage of change is the welding speed with a value of 0.7546. In other words, welding speed affects the percentage of change of tensile strength the most. And after this, using Microsoft Excel, I also generate a graph, and also it come out with the formula of this, and the prediction is done by substitution. The Y is the percentage of change of tensile strength and the X is the welding speed. After substituting, I can find out that the Y will become 0.2926 while substituting the welding speed of 60 mm per minute. This 60 mm per minute is the data that I use for my pilot test. So in short, if I use for my research, if I use the welding speed of 60 mm per minute, my tensile strength of the aluminum alloy 1100 was 110 MPa, and it will become 142.4 MPa, as you can see from here is listed. That means it's 29.49% higher than the original tensile strength. So the second part is the result and discussion for the micro hardness distribution. So I listed from here the upper part for experiment. I want to mention that the experiment 1 from the literature, they built a 9-layer stack of aluminum alloy. This is the source of the literature I'm taken, and you can see from here it has 9 layers. Experiment 2, they built 4 layers. Experiment 3, they built 2 layers, and experiment 4 is different. They use the friction stir additive deposition. So to maintain the consistency of the comparison, all the micro hardness between the first and 2 layer will be taken to be compared. This is because from experiment 1, they stated that the micro hardness in between first and second layer to the upper layer is different. In the upper layer, the micro hardness is getting harder. So this is why to maintain the consistency, I use only the micro hardness in the first layer. So for the result and discussion for the micro hardness distribution is similar like previously, except the micro hardness for experiment 3 decreased after friction stir welding. After that, doing the same data analysis, we can see is still the welding speed affecting the percentage of change of the micro hardness, which with a value of 0.9525. It means that the welding speed have direct effect to the micro hardness. So by using the same prediction, we can see that the micro hardness for aluminium alloy 1010 was 50.5, and after the FSAM repair, it should increase to 52.84. Summary for the comparison. This is just a prediction and it ignores other factors that might affect the result, including the two pin design, the pin size, the rotation spin, and others. So for the tensile strength, the prediction why the tensile strength will increase after FSAM is because during SFAM, multiple recrystallization event occurs and it resulting in finer grain size, and the fine grain size have greater resistance to deformation. For the micro hardness, the increase of hardness is due to when the material experiences high temperature and several plastic deformation, it also produces a finer grain size. So that's why it processes to a higher micro hardness. This is my hypothesis about why the tensile strength and micro hardness increase. For the comparison of macro and microstructure in experiment 1, for experiment 1, they use friction stir deposition to do repair. This is a different process from FSAM, but both methods they perform friction stir welding by adding other material rather than they just stir the original material. So this is why I think that friction stir deposition can also be compared together. So friction stir deposition was used to repair long and wide groove in this experiment. So the observation, so at here there are still some incomplete volume, but it's still possible to confirm complete volume filling of wide groove. The second experiment is done by the same team. They also use the friction stir deposition, but this time they use it to fill the single hole. So as you can see from this picture, most of the cylinder was successfully filled by the deposition, so it can be considered successfully repair the defect. The third experiment is they use the friction stir welding to remove the groove defect. So as we can see from the first picture, they have a groove defect in the material and it will decrease the mechanical properties of the material. After the repair, we can see the groove defect is disappear, and also we can observe that the repair area have larger welding area because the new weld nugget is already replaced the original weld nugget. Finally is the experiment 4, which is they use the friction stir welding to repair a tunnel defect. So the observation 1, we can see that there is a tunnel defect in the material. After repair welding, the tunnel defect is disappear already. For experiment 4, they also provide the comparison of microstructure of nugget zone and thermomechanically affected zone. So we can see after repair, the grain size of the nugget zone have decreased slightly, and also we can see that recrystallization occur in the TM exit. So it's also proof what I said earlier, that is due to the final grain size is produced, so it increased the tensile strength and hardness performance. So in all experiments, it shows that the welding successfully repaired the defect. And also I couldn't find any literature is available for repair welding using FSAM. It shows that the novelty and importance of my research. In experiment 3 and 4, which is using friction stir welding for repairing, even no additional material was added and only the original material was stirred, the repair is successful. Therefore, with added material in SSAM, it should show better result in repairing. So next for the pilot test, I have prepared the material, and I also fabricate the tool. The tool I show it at the picture, and this is the feature that I mentioned earlier. And also grinding, it simulate the groove defect on the workpiece. After for the pilot test, both of the pilot tests, I done 2 pilot tests, and both pilot tests use same parameter except for the rotation direction. The first one I use clockwise direction, the second one I use counterclockwise direction. So you can see this is the workpiece of the first pilot test, and it was successful, and two workpieces was welded together. And here there are some defect. Second pilot test, the workpiece they weld together, but at the end the two pin was broken. So the possible reason for this happening is maybe because the counterclockwise rotation have more resistance towards the material flow, or secondly is because the dimension of the two pin is not suitable. And the actual reason behind this, I think we should cut the material and observe the material flow. The material flow only we can figure out, because at this point I doesn't know the two pin break at which part of the material. And also we can see from the second pilot test it have more defect on the weld surface. So finally, for the conclusion, there are some of the related future work that I suggest that we can implement. The first one is the friction stir additive repair welding. So after reviewing and comparing the literature research, the friction stir additive manufacturing repair welding shows a possibility of success and improved material properties. So I think the FSAM repair welding should be carried out to prove the statement, and also there are no other available source that we can refer to. That means maybe no people done this before, so I think it will be a good experiment to carry out. Secondly is the mechanical and microstructural testing. So according to the prediction, the friction stir additive repair should improve the mechanical and microstructure performance. So like I mentioned earlier just now, the actual FSAM repair should be carried out and send the workpiece for mechanical and microstructural observation to prove the statement. Finally, in this study, the parameters to be compared are just the rotation and welding speed. However, there are a lot of other different factors like the two-pin design. The two-pin design also contribute a lot to the welding as a factor. So I think different two-pin design can be designed and test to observe its effect of two-pin on material flow. So that's all from me. Thank you. So see you in the Q&A session. Thank you.